When you first learn calculus, analyzing a function usually comes down to finding its highest and lowest points. You look for the maximum and minimum. But as you move into the more rigorous fields of real analysis and topology, relying on maximums and minimums breaks down completely. This number line plots a classic test case, the sequence generated by the formula 1 over n, where n represents any natural number. Looking at the first few values, 1, 1/2, 1/3, the geometry is straightforward. The fractions get progressively smaller. But watch what happens as n grows infinitely large. The sequence shrinks infinitely close to 0. Yet, no matter how large your denominator becomes, 1 divided by n will never actually equal 0. Because 0 is never reached by the sequence, there is no smallest fraction. It is mathematically impossible to identify a minimum element in this set. Without a definable minimum, basic analysis tools fail. If you cannot pinpoint where a set officially stops shrinking, you cannot reliably measure its size or its limits. To rigorously define the edges of infinity, we have to abandon maximums and minimums entirely. Instead, mathematicians use a resilient geometric framework built on bounds, the supremum and the infimum. Let's map this new framework directly onto that problematic 1 over n sequence. Look at this number line to define an upper bound. It's any real number where every set element is less than or equal to it. 1 is an upper bound, but any number greater than 1 also perfectly satisfies this rule. Upper bounds are not singular numbers. They exist as infinite sets of numbers outside the sequence. Shift your focus to the opposite end of the sequence to define a lower bound. 0, -1, and -2 all perfectly satisfy the condition of being less than or equal to every element in the 1 over n set. A set is classified as officially bounded only if it possesses both upper and lower bounds. Knowing a set is bounded isn't precise enough. We must isolate the absolute tightest parameters from these infinite blocks to define the exact geometry. How do we choose the most mathematically useful boundary out of an infinite selection of bounds? We identify the tightest possible upper constraint. This is known as the supremum, or the least upper bound. We push the upper bounds as close to the data as possible. The wall slides left until its edge hits exactly 1. It stops there, unable to move further without leaving a fraction in the sequence exposed. For our sequence, the supremum is precisely 1. We do the same for the lower constraint to find the infimum, which is the greatest lower bound. We push the lower bounds upward to meet the sequence as tightly as possible. For this sequence, the infimum stops exactly at 0. Even when a set lacks a defined maximum or minimum, the supremum and infimum act as unbreakable perimeters, providing absolute borders around the data. This introduces a professional misconception that easily trips up students, assuming the supremum and infimum are inherently part of the set. Look closely at the upper boundary of our sequence on the left side of the screen. The red supremum wall aligns perfectly with the solid dot at 1. Because the supremum is physically generated by our formula, it is an active member of the set. This physical contact makes it the greatest element. Now check the lower boundary at the infimum on the right. The blue infimum wall sits exactly at 0. The sequence dots approach it, but a microscopic gap always remains. No dot ever touches the wall. The number 0 cannot be generated by the formula 1 over n using any natural number. Because the infimum is strictly a perimeter and not a member of the actual data, this set possesses no smallest element. Boundaries always exist for bounded sets, but whether the physical data touches that boundary dictates if greatest or smallest elements exist. We can stress test this framework against sets that behave erratically at their edges to prove its resilience. This new number line maps an oscillating set, the sine of n times pi over 6. The dots bounce rhythmically back and forth. The pattern fluctuates, but the framework instantly isolates the supremum at 1 and the infimum at -1. Because the sine wave explicitly lands on these boundary numbers, they act as both the supremums and infimums, as well as the greatest and smallest elements. Now look at this highly complex multivariable set, defined by m plus 1 over n, where both are natural numbers. Because the integer m can grow infinitely large, the set escapes infinitely to the right. It lacks any upper bounds whatsoever. We evaluate the lower boundary by minimizing the integer m down to 1, while pushing n toward infinity to shrink the fraction. The tightest lower constraint, the infimum, is exactly 1. But because the fraction 1 over n never reaches 0, the value 1 is never included. Sets can be precisely bounded on one side, but entirely unbounded on the other. A rigid max-min mentality cannot survive multivariable analysis. This matrix shows the complete taxonomy of our sets: a standard closed interval, the asymptotic fraction, the oscillating sine wave, and the multivariable equation. In real analysis, you cannot rely on the assumption that a set contains its own maximum or minimum. Boundaries are exclusively determined by the external existence of tight upper and lower bounds. Isolating the least upper bound and the greatest lower bound is the only way to establish the exact geometric perimeter of a set. Only actual physical contact with this absolute perimeter dictates whether a greatest or smallest element exists in the set. The internal elements of a set may oscillate, stretch to infinity, or remain unreachable, but this framework ensures the mathematical boundary remains absolute.